Hello, my name is Jonathan Bisnet, and today I'm going to show you another project I've been working on. This one actually specifically for one of the classes I have, but in this one I've basically used a robot and programmed it in C to operate kind of like a function generator. It's not got anywhere near the features of a true function generator, but can show some various waveforms at a very specific frequency. So anyway, in order to see this a little better and not get too much glare, I'm going to take and actually turn this kind of on its side here. I turn it in a different fashion other than the wheel on it makes it a little awkward. It's designed to move, and this project doesn't really need anything to do with moving. So what I've got here is I have replaced the original display on this unit, which I can give you another look here at the unit. It originally had a display on it which was a 2x16 character LCD, and I took that out and replaced it with, in this case, an 128x64 graphics LCD display. This particular one is using an ST7920 controller, whereas the original LCD was an HD 44780. But it turns out that the first 14 pins or so are actually, it's plugged into the unit here, the first 14 pins or so are practically identical between those two units. In this particular case, the backlight is out here at 19 and 20, which I was able to take off here and wire into the VCC and ground of the board. So in that way I'm able to get a backlight and power to this graphics display, and I'm able to communicate with it in an 8-bit capacity like I would a 44780. And in fact the command set's actually fairly similar. It has an extended mode which supports the graphics capabilities. The robot here also has outcoming ports basically right along here where these yellow wires are coming out, which I ran them out to the breadboard and then to a ribbon cable, which I take and bring over here to another breadboard in order to fit things a little better. On this board I have a D to A converter here, which really uses an R to R array to output the voltage, the analog voltage. And then here I have a rotary encoder, which I'm using for selection and execution of the various waveforms, and I've used something akin to a debouncing type circuit with some resistors and capacitors around it. So anyway, here's what we've got. I'm going to go ahead and reset this unit. So what you'll see goes in here, comes up. At this point, when it says loading, what it's actually doing is going out and pre-building the values for generating the sine wave. I break the sine wave into about 200 points, so 50 per quadrant. And considering the floating point math involved, I actually am using a Taylor series process to calculate this rather than the actual sine value in the math library. But I generate to a table the values to use for the waveform on the scope or on the D to A board. So anyway, right now what you'll see is I've kind of got, I'll turn this here a little bit. I've got the menu showing here. Let's see if I can get a better view angle on it here. There we go. And as I turn the rotary encoder, what you'll see is it steps through each of the types of waves that this is designed to output. And there's a whole bunch of alternate waveforms that were determined based on the assignment, but intended to force some use of the thing. And you'll notice I can also turn it and go backwards through them, so that the rotary encoder is tied into some interrupt functions on this, and I'll explain that in a little bit. But then if I press the encoder, it actually you'll notice now it says it's generating the wave, and if I take you over here and we look at the scope, you'll see that I actually am getting a sine wave out of this. Now it's not a beautiful sine wave because it only has so many points involved in it. If I shrink it up a little bit here, let's darken it some. Let's see if I can fix the lighting here. Darken it some, you'll see it a little bit better. So you see we're getting a fairly decent sine wave out of this, and as an example, if I turn it 1 and ask for a square wave, we can see we're getting that, and then a triangle wave, sawtooth, here happens to be the first alternate. You can see that we can generate multiple waveforms out of this. And on the display with each of them, it shows you which waveform it's actually generating at the time. And then looking a little more closely at the rotary encoder, what this does here is it allows me to turn it, and there's little detents, as they're called, little markings that you can feel when it makes step to step. And as you turn it, if I move it back here a little bit, as you turn it, you'll see that and I know it's hard to see, unfortunately, but as I turn it, you'll see that the display changes a little bit. Changes with each change here, the waveform it's going to generate. So, and the way I ended up doing that, the way this rotary encoder is tied in. There are 3 pins on this one side here, right here. The center one is tied to ground directly. The other 2, as I said, are tied through kind of a debounce circuit, so there happens to be a resistor, and then from there another, we have the wire that goes off to the microcontroller, and then another resistor that goes to positive voltage, as well as a cap that goes to ground. So it kind of handles the debouncing, and it's a fairly decent size to support the duration I needed. But anyway, the center pin, I say, goes to ground, and then each of the other sides goes through these debounce arrays, and they are ultimately use the resistor to pull them up high. So as I turn this thing, when I turn it in one direction, say, versus the other, for each turn, both the A side and the B side either go high or go low. The difference is that as I'm turning it in one direction, one of those pins goes high or goes low before the other pin does. And if I turn it in the opposite direction, it will be just the reverse. The other pin goes high. So using it this way, saying, let's say A and B, if I turn it to the right as an example, A goes high, then B goes high. If I turn it to the left, B goes high, then A goes high. With the next turn, they each drop. Following turn, they each rise. So what you're really seeing is a rise and a fall with each turn. But by looking at the order in which they occur, do I get the A side first or the B side first, allows me to determine which direction the encoder is turning. And ultimately in my code, the way I handled that is these A and B are both tied to interrupt pins, port pins, that are designed to call an interrupt when the pin either transitions to high or transitions to low. And in my code, what I do is look at the status of the pins before and the pins at the time the interrupt occurs. If both pins at the time the interrupt occurs are different, then we're only partially through the turn. It hasn't completed the turn to the next stopping point. If both pins are the same, either both high or both low, then it has completed that next step. And at that point, whichever interrupt is firing is the second interrupt, and that tells me which direction we've moved. So, as an example, if I'm turning right and A goes high first, at that point, A will be high, B will be low, I'm going to say, okay, let me record the values, but we're only partially through the turn. When I turn it again, when I finish the turn, A will be high and B will be high. At that point, I get the B interrupt, and it's like, okay, now both values are high, so we've completed a turn, and I'm in the B interrupt. So that means I already got A, I'm now getting B, I must be turning right. Same logic works for turning left, and that really was all I ended up doing in the code to support this process. The other feature is on the other side of the encoder. Here, see if I can get you a picture. Lighting is terrible. Let's see if I can get a better picture here of the lighting. On the other side here are two pins, and it's kind of hard to see them, but there actually are two pins there, and they work simply like a single pole, single throw switch. And I again tied those through a debouncing circuit, but they go to another interrupt on the microcontroller, and in this case that interrupt is configured to only deal with the rising edge, or excuse me, the falling edge of the signal. Since these have pull-up resistors on them, when I depress the button, it grounds it out, which pulls the pin low, fires the interrupt, and at that point I can look at what my currently selected waveform is under the cursor based on my turning of the encoder and generate that waveform. So that's really how this guy is kind of tied into the overall circuit. An analog to digital converter, fairly simple device. It happens to have 8 input ports, and depending on the binary value you send, it's going to generate a voltage from 1 to 255 portions of its voltage range. So if you, or 0 to 255, so if I send zeros all the way across, it's basically going to ground out. If I send 255 as the binary value, it's going to send whatever its maximum voltage is. And then obviously any variation in there. So as an example, if this has got a 5-volt maximum on it, if I send 128 as the binary value, it's going to output a voltage somewhere around 2.5 volts. So that's really all this board does, but by constantly changing the output values, I'm able to generate the waveform that you see on the oscilloscope. Really, there isn't much else to it other than the display. Now, I had to write the code for the display myself. There are a couple of libraries out there available for this particular display on the Arduino, but they aren't really written for a Zilog EZ8 processor, so I had to look at how some of it was done and also look at how I had done code for the HD 44780 type controllers, because as I told you, they're very similar, and I was able to generally write the same kind of code for this. Now I had to go in and in order to make this work effectively in a graphics mode, I actually found, based on the way this particular robot's configured, I had difficulties reading the display. Now it is possible, there are some capabilities in the display that would allow you to read the display memory, but I couldn't really get that to function properly, and I'm sure it's a hardware issue with how this is wired up. So what I ended up doing was memory mapping it. So I create a buffer in my RAM memory that's equivalent to the 128 by 64 bit display, and then I have created a number of routines that will write to that bitmapped image and turn on various bits. And then periodically I run a refresh process, which will take and redraw it'll redraw the entire image out there, or a given block of it. I can give it the upper left and lower right hand corners of the block. Oh, sorry, I didn't do it that way. If I give it the upper left hand corner of the block and the width and height, and it will then output just that portion to the display memory. So that's really how this project worked. I'm more than willing to share the source code if somebody is interested in it. It's a work in progress. It does still contain some quirky little bugs here and there. I may work on fixing some of them. At this point I really don't know, but I would be more than glad to share the code if somebody's interested in taking a look at it. Anyway, I hope you found this interesting, and I look to do some more. Talk to you later.